I forgot to do that. And like I said, I didn't plan on being
Did he
presented anyway.
Did he reach out to you? Because I thought that mine, when I sent him mine on Friday, I thought that it like didn't send through, so I emailed it to him again on Sunday, and he was like, "Oh no, I received yours. I sent out a letter to Aaron. Did that go to you by chance?" But it didn't, so I'll just make sure that he got a hold of you.
He might have. I could check.
Because he just needed like one slide to present like 3 minutes on at the beginning of the event.
Mm-hmm.
As far as printing goes, do you just like, are you just using Office Max or something to print out your poster?
NDSU has a poster printing
Oh, they do?
service.
Oh,
in,
cool.
What's that building across the street from Dunbar?
IAC? Or Quentin Burdick?
Yeah, Quentin Burdick. They have a printing center in there.
The barbecue building.
Or barbecue.
Yeah, it used to be Quentin Burdick, and then they changed it to IAC.
Well, thanks much for finding it possible to come. We will do have an event this Thursday and Friday, right? And we better help each other to improve the posters. John, even if you haven't registered, you're welcome to come and whatever, apply for reimbursement, which will be covered if you just want to stop by and chat.
Okay, I think I'll probably end up doing that then. I'll talk to Levi and make sure he's around.
Okay. So, how to print? Do you know Amy, who is the chemistry secretary?
Yes.
So if you approach her, she should be able to either help herself or direct you to Diona. Well, they have a network of like administrators. They issue, well, you can print on your own and then submit for reimbursement, but they can issue a form which will, like a voucher for free printing. Well, it's not in fact free, but it will be free for you. And with this voucher, you're coming to this QBB first floor in a reasonable time, not in the middle of the night, but like before 6 p.m. Probably before 6 p.m. on Wednesday, because the actual conference starts on Thursday, and they will print. Also, there is a printing service in the Memorial Union, but then you need to pay and then apply for reimbursement. Okay? And I'm just thinking of myself. If you prepare a poster until last minute and it is ready only like 5 a.m. at the day of presentation, one can go to any FedEx Kinkos that print in the middle of the night or whatever. What else? Do you know your schedules when you need to present?
Mm-hmm.
Yeah, I think I'm third. Are you talking about like the 3 minute like
Yes.
overview? Yeah, I'm third on Thursday.
Did you all send the one slide summary? Do you plan to do it?
I think he already compiled them.
Okay.
He sent an email saying like he was going to compile them all.
Those are the abstracts. The thing that he sent out yesterday. Those are the abstracts. That he
Do
compiled.
not hesitate. Just take your name, title, and maybe one most attractive picture and put it on one-page slide. So it's like 2 minutes work.
Okay.
Do not feel much responsible for the content. So I have printed copies for everyone. So we'll just listen to presenter and make the comments. John, you may, I don't know how you will arrange it, but you can collect comments by handwriting or whatever and then share it by email. And feel free to stop the presenter. We are not in a rush for only 3 posters and 2 hours limit, we can be very relaxed and you will finish early.
Okay.
So, based on today's meeting, please try to return your feedback to authors. Authors implement and print tomorrow sometimes. Okay? I have no idea where you need to hang the posters. Probably you will figure it out. What do we do next? Tuesday. It is too early for the GRFP, so probably GRFP will go in 2 weeks. And next Tuesday we'll look for open deadlines for conferences other than Sanibel. And also I have to write a proposal and I may invite you to help. Just bringing in, I don't know, like page, paragraph, 2 pages, whatever, so it will be things that John and Aaron are doing, so on perovskites. But all of us can contribute something there. So proposal and future conferences next time. So how do we do the presentations? We have both PowerPoint and PDF of the posters, so you can bring your slides up front and just focus our attention to whatever you need to discuss about, right? And then you, because the whole poster will be not visible, and then you can just browse through and point our attention on necessary part. Okay? So Aaron, Yvonne, and then Dane. So you have, please feel free to start, and I will distribute materials as we go.
So I'll be presenting on perovskite quantum dots with using them for applications and enhancing their photoluminescence properties through doping with a manganese ion. So light halide perovskites have been popular for the last 5 years or so because they're good absorbers and they're cheap to make, and they have tunable emission, so you can use them for optoelectronic properties. And the one issue that arises in perovskite quantum dots is that over their, what's what I'm looking for? They can have a short lifetime, for PL lifetime, due to degradation, to either through moisture or through oxygen degradation or just through phase transition. So there's been motivation to try to get stable emission out of these perovskites. And then one method that's come recently is through manganese doping, which has been popular in other semiconductor quantum dots as well. And then recently it's been shown that you can get stable emission from introducing manganese dopants into perovskite quantum dots. You can get stable 600 nanometer emission, so roughly orangish red emission out of these. So the purpose of this presentation is to characterize the method that these perovskite nanocrystals luminesce. So basically their ground state electronic structure, the spin configuration of the manganese dopant, which will be important for the mechanism as to how it photoluminesces. And yeah, those are the main things that we're going to be looking at. So the hypothesis that we started out with when we went into this is that due to the crystal field splitting of the manganese ion being inside the crystal, that we would see substantial crystal field splitting. So for the manganese ion, there's 2 spin configurations that it likes to take, either a high or a low, or sextet or a singlet configuration. And we figured that the sextet or the singlet configuration would provide the necessary energy offset to get the 600 nanometer emission from the perovskites.
Fonts are general suggestions. It's matter of taste. Even if printed large, it is too much of continuous text. Most of, well, not most, but about half of audience can be impatient to read through long sentences. So one may decide to do broken, like bullet points.
Yeah.
Something that one can skim through without looking where is the verb, where is the end of sentence. For crystal field splitting, the what you show as sextet here shows 0 crystal field splitting. This will induce objections or questions. So you may explicitly introduce this delta. You may show the schematic of which ligands are interfacing the magnetic ion, and even maybe without math, because we do not have space, but explain main principle why the orbitals are splitting, and what does it mean low spin and high spin.
I was just going to write down notes for myself.
Another thing too, as far as like the font itself goes, it might be good. I gotta do this myself, but it might be good to use a font with feet on it, like Times New Roman. It just makes it easier to read things on paper.
That has feet.
Yeah, so like right now it looks like you're using a Calibri font. If you were to use one like Times New Roman, your H would have like a foot on it. Like we learned it in our writing in the sciences course that on paper you want to use fonts that have this rather than this for like paper. This is more for like online reading. This is on paper font.
Okay.
Something to consider.
John raised.
Yeah, so I just have one comment, one question, right? So I'm assuming the manganese is doping for a lead, correct? So it's going to be octahedrally coordinated within the system? Okay. Another thing to potentially look at is for specific geometries of dopants so the geometries can direct the levels of splitting that can occur in the crystal field. Off the top of my head, I don't remember what first row transition metals like gravitate more towards, but it might give a good idea of what you might expect. And just another piece of information for you to back up whatever you find.
So it's not very coordination of the manganese.
Yeah, it can definitely play a role in which type of splitting is prioritized.
No, it is not visible for John. I think he means image like this in the upper.
Right, yeah, that's kind of.
And
But I jotted down
in the audience of professional chemists, it will be most appealing.
Oh yeah.
So did he show you like some kind of like delta O or delta? Is that what you had drawn, Dr. Killen?
Yes.
Okay. Yeah, because one of the other things I guess that I was thinking more along the lines of is the difference in coordination chemistry for something that's changing the splitting can actually direct high versus low spin, which in this case, it might be pretty straightforward, but that's also another thing to kind of check into.
Okay. And so then, going off this, I planned on making a figure that took single point calculations from VAS for just forcing it into each spin configuration, and then showing that the minimum is going to be for the sextet configuration. So that'd be kind of blocked off in this area. So that gives motivation of why we're investigating a specific spin configuration in these systems. And then NERSC was down for the weekend, so I wasn't able to generate dose and spectra for all these.
You couldn't report it on the conference.
Right. Well, I planned to do it this weekend, and I sat down Friday.
Fine. That's fine. You can do nice presentation without any results at all.
So then, yeah, those would be comparing the spin polarized versions with the spin orbit coupling, because we can see, well, going over on the right hand side for our spin dependent configurations for the dopant.
Methods first, results second.
Okay. So
And same, you can also swap in your like spatial arrangement of material.
I should move the bottom
Bottom
panels up.
Yes.
Okay. So yeah, we calculate the dose just by sifting through the energies of all the orbitals and then counting the number of states for each energy. Then we do calculate our absorption spectrum by doing this, sifting through differences in energy between all the orbitals, and then weighting them by the oscillator strength, which isn't shown presently, but that just gives the probability of transition occurring in these systems. And then my methods are still a little bit lax, but to compute the excited state, or how do I want to say this? We want to compute the quantum yield after excitation of the system. So we have to take a specific excitation, and then we allow the system to relax to the HOMO-LUMO band edges, or the electron and hole to relax to the HOMO-LUMO band edges. And we do that using excited state dissipative dynamics, shown in these equations here, where the first term is just your normal time evolution for quantum states, and then the second term is the dissipative, which is the electron losing energy due to phonon interactions in the crystal. So that relaxes the excited electron down to the band edge. And then we can compute just changes in occupations by counting the electron density for each energy levels. And then while the system relaxes, we can also compute the probability of radiative relaxations as it's decaying. So basically the electron decays a little bit, and then we track the probability of photoluminescence occurring between electron and hole at that stage, and we just keep doing it iteratively until it relaxes to the band edge. And then eventually we compute the quantum yield, which I don't have shown on the equations yet, which I plan to implement.
Questions? So everything is correct, everything is right, but there is an impression that you are hiding most impressive details, either for brevity or because you do not feel 100% comfortable with them.
Probably mix of both.
But in the audience of visitors to the poster, you will be the world star. You will be best expert in this area. There will be few other people who just blindly run ab initio software like a black box. But you can pose yourself as a big leader who knows something above just plain use. So even you do some mistakes, no one will realize. And you will look very favorable if you show something that makes you to stand out from the average. So do not hesitate. Even if you do some little mix-up, that's fine. It is more important to stand out. It's better than just hide it. Generally, you do whatever you like, but you can get benefits of being how to say,
Stand out.
self-advertising. Spinners, what are they?
They
Do not answer me. Just plan to introduce.
okay.
And you can be teacher of 100 visitors to a poster about spinners. It's not a secret for last 80 years, but most of people, even who do calculations and call themselves theorists, either do not know about them or try to avoid them, because avoiding intellectual challenge. So if you just tell a little bit, you will stand out again. So even if you tell about the method details and tell about spinners and declare your goals, stop. You're already a hero. But if you add something meat of the results, it will be true standing out in square.
Mm-hmm. Yeah, it all makes sense. I guess. Well, I'm just kind of hesitating because I haven't thought about how to lay out the narrative yet.
Okay.
So it's
But
like
do not. You will be the best expert in the field in the audience. There will be no you see other experts here in the room, right?
Mm-hmm.
All others will be less prepared to speak about the subjects.
Okay. So then, yes. How do I zoom out here?
Just this finger, or 2 fingers.
Oh,
This.
there
Yes.
And so, again, I'm just trying to frame. So, initially, since we've figured that the low spin contribution, whereas the photoluminescence would come from, we would do spin polarized calculations for our orbitals, which allow spin, or which doesn't require spin flip transition, so we don't need spin orb coupling. So we would expect transitions from either spin alpha to spin alpha states or spin beta to spin beta states to account for the correct band gap that's seen experimentally. But what we find is that the spin allowed transitions are either too wide or too narrow to account for emissions coming experimentally from the doped perovskites. So that means that we have to have spin forbidden transitions in these systems, which necessitates the need for spin orbit coupling in spinor orbitals to describe them, which is shown with this arrow here. And we can see that for the spin forbidden transition, it's going to have a high probability of occurring too, because the HOMO is on the metal ion itself, and then the LUMO is on the manganese metal ion itself too, so it's a metal-metal transition. So it has very high probability of occurring. And I guess I'm not quite sure what more else to say at this point on it.
Let's discuss. Ask some tricky questions to Aaron.
I guess I have a question for myself. So
Please.
I know so it seems like the occupied orbitals, the metal ions, they have like a high degree of splitting between their states. So you can see that there's only these two are centered on the manganese, and the perovskite HOMO is here. So that must mean that the other 3 occupied on the manganese must be below the perovskite. But then for the LUMO, all the spin states, they're basically degenerate. There's like a 1/10 of an EV gap between all of them.
Mm-hmm.
It just seems odd to me because it seems like a mix.
So you see beta 3D orbitals of manganese, and you miss 3 out of 5 alpha 3D orbitals of manganese in this image.
Mm-hmm. Yeah, they must be within the conduction band of the perovskite.
I have some idea how to address it, but do we realize the problem?
No.
No? So there should be total 5 orbitals with spin beta and 5 orbitals with spin alpha that are sitting on the d metal. So for beta, well, first Aaron didn't declare, well, it is kind of self-evident, but it's better to declare that although main calculations and main results deal with non-collinear results, non-collinear data, this diagram shows only spin polarized. Spin polarized. Polarized data. And then we do have a contradiction between our intuitive expectation or diagram from a textbook, or these 2 and 3 orbitals are split by delta octahedral. And the fact that the energies of alpha orbitals and beta orbitals are very non-equal. So on the diagram here, we draw a level, and then we can place an electron up or down, or same as you do here, right?
Mm-hmm.
But in fact, if you run for spin polarized calculations, instead of such figure, you will first have 2 sets of figures. One for spin alpha, where it will be up, 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 and then second for spin beta, for down, down. And then with calculation, with self-consistent cycle, you will see that the alpha and beta orbitals, which we show the same energy, can, like alpha orbitals, can drop much deeper down, so that they will be masked, they will be hidden inside the conduction band, well, inside the valence band, composed of iodine 2p states.
Mm-hmm. Is that? I guess initially,
yes.
I guess initially I just thought it was some sort of hybridization effect, possibly.
No. This feature pops up in most calculations with magnetic materials. If you look onto...
Sorry, did you say magnetic materials?
Yes, magnetic. So if you have different number of electrons with quantum number alpha with up and down, each spin has magnetic moment and will feel the magnet. So you can, well, if you have just one magnetic ion, probably you cannot move it too much in space, but if you put more of those, you can just pull this quantum dot out of solvent by a magnet. Or at least see some floating towards a magnet.
So as expected that there's supposed to be 3 pairs of spin up, spin down, but that's not the case, and that's where the confusion comes in? Am I right to understand?
Yes. Okay. Actually 5. You know, number of 5 of d orbitals is 5. And for spin down, Aaron does see that there are 5 orbitals. But for spin up, there are only 2. And
yeah, show up within the gap anyway.
it is a confuse. A message personally to Aaron. If you look on Hugo, well, Hugo is his It's not in formal name, not in paper. G with G. I never called him in his passport name. What is his first name?
Cool.
G.
Yeah.
Okay, G Yao. And he agrees. Well, Yao. G Yao. I shared his paper last night with you, and if you look on Figure 4, it does show the image, the typical image of spin polarized density of states, and it shows same as we always do: occupied and unoccupied, conduction band, valence band, and for deep in the valence band and up and very high in the conduction band, those are symmetric. Those. But inside the gap, they are very unsymmetric. And well, he didn't work with d orbitals. He worked with f orbitals. But those that are, he also had very polarized, same like 5 unpaired electrons. He has this case. It is one before European. In periodic table, the lanthonide that is
Gadolinium?
no, gadolinium is one after European. It has 7.
Samarium?
Samarium, yes, for samarium. SM3 plus also has 5 unpaired, and alpha electrons are very close to valence band. And as we show, as we symbolize them with, field, they are seen at this. And unoccupied F electrons, they are shifted by, I don't know, like 4 electron volts towards conduction band. So this is a manifestation of the effect that we have energies of alpha and beta electrons are very non-equal.
Okay, so just from this diagram, like this red peak is just shifted to the left a little bit more.
So what to do? If you do PDOS image for spin polarized, you will see where are the rest of manganese d orbitals.
So what's the band gap for this material without doping?
Without doping,
Yeah.
it would be be like 2-4.
I guess maybe that's the reason. Because for Hugo's work, for sodium neutral fluoride, I guess the calculated band gap may be like 6.
Yes. And then all alpha and beta
Yeah.
were inside the gap,
Yeah.
but they were offset by like 3-4 eV. So if the manganese alpha orbitals, they can be like 2 electron volts below the Fermi energy inside the valence band.
Okay, I'll make sure to make that figure. Investigate where those orbitals are. And so I guess that somewhat resolves that question. Any other questions on this figure?
Oh, not on the figures,
Oh.
but on the presentation itself. So, because Dr. Gillian said that there's not going to be a ton of people professional on your specific topic, how, like, if I were to come up with no background knowledge of what's going on here, why would I be interested in it? Like, what do your results prove to help the scientific community?
These are preliminary results for, well, ultimately we want to calculate quantum yield or quantum efficiency or photoluminescence efficiency in these systems. So that's the ultimate goal. But up to here, we haven't gotten that far yet. We just calculated ground state electronic structure. So we've kind of nailed down what electronic structure this system likes to be in. And we know the mechanism for the electronic transitions that occur. So we figured that out, and then the next is doing the dynamics and then doing the excited state electron dynamics.
About like real world applications.
More strategically.
Yeah.
Oh, like practical applications?
Yes.
Oh, well, I mean, normally without doping, these quantum dots, they're good emitters, but they tend to have short lifetimes. So if you put manganese in there, you can get stable emission for a longer lifetime of a desired wavelength.
So like they could use these quantum dots in like these new televisions and stuff. And
Exactly.
Longer,
Yes.
Longer lifetime for them.
Yeah, could be used in televisions. Well, you'd only have one emission, so you couldn't do all the colors, but you could do lasing, like optical electronics. Like if you just wanted a short pulse of a 600 nanometer emission.
Sorry for touching it without your permission. So, Aaron presents results which already have a lot of investments into developing a structure that mimics what people are trying to do in experiment and tries to do best possible in the world surface coverage of these quantum dots. The main enemy of good light emitter are surface traps. So the orbitals that belong to intrinsic iodine or whatever, bromine p orbitals here, and lead s orbitals are, for best emission properties, must be localized in the center of quantum dot. But see, even if it is very carefully designed organic shell, they look like a little threads, so they like to localize close to the surface, which means they will be not ideal for emission. On experiment, you just do a dirty and silly work. You repeat synthesis again, do many samples, and 1 out of whatever, if you're lucky 5, or if you're unlucky of 1,000, will be bright emitter. The rest will be garbage with this surface states. And if you look to industry, it's not good. It's too expensive to do too many attempts. But if one places a dopant inside, no matter what is on the surface, it will emit, because it is, as Aaron is showing, it is transition from metal to metal. So, does it answer your?
Yeah, absolutely. I think that when you give your like 2 or 3 minute oral introduction on your poster, that'll be important to talk about, seeing as there's not going to be a lot of people that might be interested in it. It'll be like important to make them interested.
Mm-hmm. Yeah, that'd be good. Like, if people just want the highlights,
Yeah. I
what's
think,
important
just
about this.
make people think that it's some crazy new, like convince them that they want to come to your poster out of all the other hundreds that are going to be there or whatever. Tens or whatever, however many people are going to be there. I don't know. It's my only comment.
More questions? John is about to design a question, but he is not sure which one.
So just after, this discussion we've had, so am I reading this right? So when you look at the 5D orbitals that you have in the beta spin, that they are, well, I guess I'm a little confused on the labeling you have. So you have the LUMO of the quantum dot for beta, you have the HOMO of the quantum dot, and then you have the 5D orbitals in between them. So are you saying that these are like vacant or filled, just asymmetrical in the gap? Was that the discussion when you're talking about the spin polarized density of states?
I guess I missed what you're trying to get at.
Like, okay, so the initial question is, are the 5 d orbital splitting states that you show for the spin beta, are they filled or not filled?
These ones up here? Or where's my pointer?
Yeah, whatever the set of 5 is.
The green ones, yeah, those are unfilled.
Those are, okay.
Yeah, they don't have an arrow with them, so.
Okay, so are they lower in relative energy compared to what you have labeled as the LUMO of the quantum dot?
Yes. The LUMO of the quantum dot is roughly about 0.
Yeah.
0 eV from.
Okay.
I see the confusion. So the on the left hand side you see the arrow with the energy listed at each one of those levels, and the 5 spin beta isn't labeled, but all the other ones are. And the one between -2.34 and -3.14 is not labeled either.
Yeah, I guess I see what you're saying. I guess when I was going through it, I thought it'd be too busy if I put numbers for each of them.
Because yeah, I mean, right. So I mean, I guess I would at least put in maybe like a small cartoon figure that just shows the relative energies of all of them, because it wouldn't make much sense to have something labeled as the LUMO with unoccupied states below it, just kind of without anything to indicate what you might be trying to highlight.
Mm-hmm. I guess I see what you mean. Like I've been working on it for a while, so it makes sense to be a LUMO quantum dot, LUMO manganese, but it probably wouldn't be as clear to others.
Right. So I guess my other question is, so when you have it labeled as the HOMO for the manganese, I mean, so that's just the highest occupied of the manganese itself, but should it also be listed as the highest occupied of the quantum dot?
Well, I guess in my brain I partition it between states occupied on the quantum dot and the states occupied on the manganese ion, or that's due to the manganese ion.
Okay. So I mean, so I guess the way you think of it is more of like the core shell type idea, where you have 2 separate fragments. Okay.
Right. It's like
because
orbitals on
with just
orbitals intrinsic.
Okay. Okay. Yeah, I mean, it could be misconstrued just a little bit with, since it's only a single atom dopant, some people would potentially consider that just, part of the quantum dot. So, I mean, I now understand after your explanation, I understand where you're coming from, but that could also be something that people might be a little curious about.
Mm-hmm. Yeah, there's quite a bit I could be more explicit on in the poster, or make more visually clear.
Oh, that's okay. You got a couple days yet.
Yeah. I'm on Friday too, so I have an extra day.
Oh, okay. Can I approach with your permission?
Feel free.
Thank you. John? Do you see the poster?
Yes.
So, no, you don't.
No, I don't.
Let me come to the notation mode and make something that will partially address some of your questions. So I would put there LUMO alpha, HOMO alpha, and here LUMO beta and HOMO beta, because they sometimes they're not equal.
Mm-hmm.
Make sense?
Yeah. Yeah. No, I'm good with I'm good with that. I was just a little bit curious on the relative energy within beta itself on where the d orbital splitting was occurring.
Okay.
That energy difference wasn't.
Well,
clear.
I think Aaron did labeled the values of energies and aligned orbitals not randomly in the space of poster, but putting them higher or lower depending on their relative energy.
And they're aligned with the numbers. You can
Yes, yes, aligning with the numbers. So this figure is twofold, has twofold benefit. On one hand, it is energy diagram, explicitly showing difference between alpha and beta orbitals energy. On another hand, it is spatial distribution of orbitals.
Maybe it would be beneficial to put another y-axis on the right-hand side specifically for the green figures, and then have the left one just for the yellows for your values of energy. It might make things a little more clear. I don't know. I like what you have right now. I understood, but
Yeah, I mean, mostly I'm just limited by, like, not making the orbitals or the pictures too small so you can't resolve the orbitals. Because I would have to make them probably a little bit smaller to fit in that space, but I can play with it a little bit.
I
too.
mean, like, if you like keep it just how you have, but just add another energy axis just to the right side, so you could have your alpha energy scale and your beta energy scale on the same. You know, keep them all just how you have them right now. Just throw another one on there, maybe.
Right. Or
I get
just
what you're
throw
saying.
in.
If I put one in
Just
here,
say- or
I have
just-
to scoop this over, and there's not really a lot of room to move it over unless I decrease the size of all these.
I mean, or just throw in a Lumo manganese in that section of 5, because I think that would, after discussion, that would clear things up.
Okay.
Yeah, I could do that too. That's probably be
Yep.
the most consistent way with what I already have.
More questions?
Did 40 minutes on my poster. Wow.
Okay, let's thank Aaron for investing 40 minutes into the poster.
John's got one more.
John, did you have more questions to Aaron?
Well, no. So just from your initial results, I mean, are you saying that yes, this does indeed go to high spin?
Yes, the sextet
Right, given-
configuration is the most energetic.
Okay. Okay, perfect. And when I was thinking about what I had said earlier, so given that you have an octahedrally coordinated manganese with iodine surrounding it, so iodines are usually like kind of like weak field splitting ligands, and if you just look at like ligand field splitting theories, it should direct towards the high spin that you did see. So that's just in case you need a little chemical basis for initial hypothesis.
Mm-hmm. Yeah, that's a good thing to mention. I know I did play around with doing chlorine too to see if I can get extra splitting from those, but those are basically sextet as well. So there wasn't a big change depending on the halide that was used.
Okay. Ketones. Do not close it. Do not close it.
Okay.
Just put it out here.
Minimize.
Yuan, would you like to show your? Let's check around it.
So this is what I was trying to say. So like, this one lines here.
You can just by fingers. You can, if you would like to.
Lines here, right?
expand,
So you
because
got
this
three
size we don't see
values
much.
important to your yellow. Maybe you could use one right there. What I was
Yeah.
trying to say is just you can just have another energy scale right on the right hand side with your values there, and there.
Mm-hmm. I get what you're saying, but it's just I wanted to squeeze that one in with the numbers on the side. It's like
You could consider going from a 3x3 to a 3x4 poster too.
Okay, so basically in this study, we are using time-dependent excited state molecular dynamics to investigate the photo-induced reactions of cyclohexane. And I guess the most important result is that in our simulation, we observe several reactions, including photopolymerization and also hydrogen dehydrogenation. So here is a brief introduction about time-dependent excited state molecular dynamics. So basically, we start with our simulation with the one electron Cauchy equations. By solving this equation, we can get the orbital and orbital energy, and the time evolution of electronic degrees of freedom can be calculated by solving the equation of motion according to this equation. So here the first term is the Fock matrix, Fock operator, and the second one is the density operator. And here this is the electronic dissipative transitions. So for the Fock matrix, we have three components. The first one is ground-state Fock, and then we have night-band coupling. The third one is the light-to-matter interaction. So this term is time dependent, but by applying some approximations, we can treat it as time independent. So based on Rabi theory, the Rabi frequency is related to transition dipole moment and the intensity of electrical field. So due to optically driven Rabi oscillations, I should switch this to, but so we can have hops in the element of density matrix so that we can have stepwise change in occupation of two participating orbitals. So with this equation, we can update the electron density. With new density, we can get new atomic forces. With new forces, we can get the nuclear position. So in TD-SMD simulations, the electronic degrees of freedom is coupled with nuclear degrees of freedom. But there is one problem. So in TD-SMD simulations, the system has relatively large kinetic energy, so that there is bond elongation or bond contraction events. So we, in addition to TD-SMD simulations, we apply a post-processing technique. So that is, at the end of TD-SMD simulations, we extract the intermediates from the trajectory, and then we save these intermediates and apply additional geometry optimization so that we can minimize the bond contraction or bond elongation events, and also to remove uncertainty of the total energy. And after we apply this post-processing technique, we report the geometry as well as the total energy. Okay, so here is our result. So this is just a basic electronic structure for our initial input. So basically, our cell consists of two molecules, and we consider two configurations. The first one is two molecules is placed face to face, and second one is molecules in side-by-side configuration.
Yeah. Can you give a very brief introduction before we go to technical details? Same question as Dane was asking to Aaron, like why this project has been started.
I guess we have two reasons. So the first one is experimentally, some groups have found by applying UV irradiation, this liquid cyclohexane can turn into solid silicon. And I guess the second reason is we want to prove our TD-SMD simulation is, how to say that, is very powerful. It can be used to simulate photo-induced process like photofragmentation.
Okay, so you do not have any references to the designers of this molecule.
Not really.
So you may add because they may come in person, and you want to give them credit. So they all work here.
Okay.
The main challenge, scientific challenge that they addressed in the past is that they found a way to fabricate this cyclohexacillane. Theoretically, it was clear that such molecule exists, but they found a way to fabricate it efficiently and stabilize. And then you may like copy paste from their paper a photograph of like a beaker with this transparent liquid, And this is ink. It can be used as an ink, so you spray it onto a circuit, then apply UV light, and it becomes crystalline silicon. So you can, instead of etching semiconductor circuits, you can draw them by a pencil or by a robotic arm or whatever. And so main achievement was to design a way to fabricate this ink that polymerize under light. And now we are trying to contribute to understanding of the background process, how does it polymerize. But it was not trivial to find and stabilize this molecule. And they're extremely proud of it. Please keep going.
Yeah. So I guess one of the most important message we can get from here is the band gap between home and lumen is pretty large. So for our initial input, the band gap is maybe 4 electron volts.
Which color?
What?
Which color of the visible range does it correspond to? How does this molecule appear visually?
Transparent?
Yes, so it's UV.
Yeah.
Absolutely. Okay.
So next, by using the previously mentioned input, we run TD-SMD simulations, and then we apply post-processing technique. And here, so A, B, C, D, this is from one trajectory by using the face-to-face configuration. And I guess the most important thing is for the first figure, we can clearly see there is, I guess maybe polymerization is not the accurate word, but maybe dimerization happens. So, and another interesting point is, if we look at the terminal atoms, we can find there are 3 hydrogens. So that means in our simulation, we not only have the ring opening, but also we have the hydrogen migration events. And for other figures, we can see the dehydrogenation. And for the bottom 4 panels, these are from another trajectory by using set-by-set configuration. And we can see the very interesting 4-member ring and also 3-member ring. Yeah, my final result is the simulated mass spectrum. So from TD-SMD trajectories, we can just build the simulated mass spectrum. And so the most strong peak is the single molecule peak. But in the high mass regime, we can see there are many high mass peaks. So this provides another evidence we have dimerization reaction in our simulation. Yeah, that's it.
Okay, let's thank you. Any questions? So how would the mass spectrum look if there is no reaction?
I guess if there is only fragmentation instead of dimerization, we can only observe fragments with mass less than the single molecule.
Okay, so what you want to say that from initial reactant,
Yes.
there is this direction is fragmentation and this is polymerization.
Yes.
And you probably can even mark it on a poster because some visitors will come for very short interval of time and they may have doesn't want to put the marks by some reason. I don't know. It's on the edge, but one can make an arrow showing that one side it is fragmentation, and another is polymerization.
John had something.
Yep.
So, I mean, just kind of a quick question. So, when you're looking at these two different orientations of face-to-face or side-by-side, is there one that polymerizes faster than the other? Like, if people are interested in, how long is it going to take for this to happen? I mean, I know it's under, it's inside a picosecond for trajectory, but did you see one happening faster than the other?
Not really. Because right now we run our simulation for a time period of 2 picoseconds. And I guess for the face-to-face configuration, the dimerization is occurring at maybe 1500 femtoseconds. For the side-by-side configuration, it's maybe similar, maybe 1600 or 1700. So I guess there is no huge difference.
Okay. And then do you think that, I mean, once you hit a laser, I mean, with UV light, I mean, do you think there's something, if you would take it right at the absorption onset, or do you think if you'd use like a specific wavelength a little bit higher, you could change how fast the reaction would happen?
Yes, absolutely. I guess it is wavelength dependent. So right now I'm just using, I guess, the first 3 transitions with the most oscillator strength.
Okay. And then do you happen to have which wavelengths those are that correspond to those oscillator strengths, like marked?
Not really. I guess maybe it's in the range of 5 electron volts to 6 electron volts.
So if you would use like hybrid functional, you would come maybe a little closer to reality.
Yeah.
Or you can take products of reaction and analyze them with like Gaussian MP2 or TDDFT for spectra. Okay. So you are modeling 2 monomers with maximal size of the product is silicon 12.
Yes.
What does happen in reality, and what is the target product for applications?
I guess in your case we should consider a liquid.
Okay. But liquid composed of this silicon 6 is a reactant. And what is the product? What they typically try to obtain?
I remember one of their findings is, so they have this kind of molecule, and this molecule can undergo dehydrogenation, and then they end up with just a crystal of silicon.
Yes, crystalline silicon, infinitely large or some confined.
Yes.
Well, they can do printed circuits of infinitely large, but recent things.
I saw that it's a quantum dot.
Yes. So if you let it grow intermediate lengths, it will grow into quantum dots, which are other fun objects to do. John, your co-authors, Dr. Hobby and Sam, and quantum dots that you computed for them for publication were fabricated with this method. So
I just say after the local ACS up in Fargo, Eric had kind of mentioned that they had been using this to generate their crystals.
Yep. So you are in some sort of end user of this technology.
Do you know, and I guess this can go to Yulin as well, so being able to use this type of cyclosilicon compound, is the growth rate of these crystals enhanced, or is the size distribution of the crystals more manageable using this type of molecule versus typical like silane gas that they might use?
I have no idea.
I don't know. Probably they do some centrifugation after they're done, but it doesn't generate monodisperse. It creates anything, and then you need to do a homework on separating the products. Heating. Were you able to see polymerization just by heating it?
I didn't try it.
What is the barrier? So if they really want to polymerize, maybe upon elimination of hydrogen, they are attracted to each other rather than repelling. The activation barrier for this polymerization shouldn't be very high, because you get it again and again at different conditions. So maybe even with moderate temperatures like 1000 Kelvin, it will be sufficient for them to fuse.
Yeah, I can try that. But so for TD-SMD simulations, I try 3 trajectories for face-to-face, and I found only one have dimerization. The other 2 molecules just repel with each other.
Okay. Good. More questions? Fatima? You are doing calculations on silanes, so you will have some questions.
Can you please explain a little bit this figure, like how you this post-processing?
Which figure?
This one. Yeah. The steps.
So, what's your question?
This
How to process?
This time-dependent excited state. What is?
Molecular dynamics.
Yeah, molecular dynamics. Like, what does maybe like saving intermediates mean? Like.
So, like you do molecular dynamics, you have at each time step you have a set of nuclear positions, right? So what I did is at each time step I extract these nuclear positions and then put it to another folder and then run geometry optimization to these intermediates.
Okay. Is this something different? Like,
Please
what
keep
I-
asking.
So is it something different, like what we? I'm not sure.
Yeah, this is something that Dr. Han has came up with. So he determines the intermediates based off off the atoms' proximity to one another. So if they're within the bond distance, he considers them to be one intermediate, and then he goes and takes each one of those intermediates and runs geometry optimization.
Okay.
But this procedure TD-SMD is not included into standard software.
Okay.
It's like unique software with Dr. Han being
okay.
author or one of authors, so it's a unique procedure. And the arrow that goes from one box from left to the right, why do we need this optimization? Because during the high energy dynamics, the trajectory includes very unstable transition states, which there is no sense to analyze them, and they are unstable. They can decompose one or another way. So one needs to bring them into more stable configuration and then see what are they.
Okay.
Make sense? I think Dane is the strongest chemist in this audience. like professional education. More questions? If not, thank Ivan once again. Floor is yours.
So, would like to start out by saying that my introduction is probably the weakest portion, in my opinion, of my poster. I have too much writing and too many sources, I believe. I've got 23 sources in my introduction alone, so I need to downsize that, obviously. Probably simplify it into important bullet points. But, alright, so we'll get started here. So, purpose of this research is to increase the stability of rocket fuel used in unmanned spacecraft. So currently, the fuel that we use in unmanned spacecraft is most favorable for space exploration when it comes to efficiency and price. It's not only easier to move spacecrafts with hypergolic fuel in comparison to cryogenic or petroleum fuels, but it's easier to store. The main difficulty with it right now is its toxic byproducts, and one of the challenges that we know of regarding these toxic byproducts is the level of toxicity that is within the product after combustion of this hypergolic fuel. Specifically, hydrazine and dinitrogen tetroxide, DTO being the oxidizer and hydrazine being the fuel. So what the goal is here is to understand what mechanisms are occurring and to give values to the amount of toxic byproducts that are being created, as well as determine the mechanism for the formation of water molecules. We're interested in water molecules specifically because of the stability factor that they provide to this reaction. So in order to determine this mechanism, a simulation cell was built using Avogadro, and molecular dynamics were calculated using VASP software, and then this was visualized using VMD software. So to start out with the simulation cell, we used a 1-to-1 ratio of fuel to oxidizer using high temperature and high pressure, specifically 3500 Kelvin and 729 cubic angstrom cell. So this is pictured here on the bottom left. You could see an initial time step of 0. So that's what the cell looks like. Initially, there's 4 hydrogen, 4 dinitrogen tetroxide. Yes, sorry.
So I pretend I know nothing.
Yeah.
So you are showing cell size.
Yes.
Does it mean that you do not have infinite amount of vacuum? It means you use periodic boundary conditions.
Yes.
Good, correct.
Yes. Okay.
And be ready to answer what they are.
Okay. So what are periodic boundary conditions?
What are periodic boundary conditions?
So periodic boundary conditions, if not being used, says that your reaction is confined to the simulation cell, whereas in this simulation instead, it's unit cells basically reoccurring at each boundary. So if the combustion allows for the molecules to go through one side of the boundary, it'll appear again on the other side of the reaction cell.
Excellent.
Okay. So where was I? So we'll go. All right, my methods are pretty poor right now as well. I realize that my equations don't even go in numbered order. I'm missing a number 5 equation, and I like.
I read the saying like, "What a humble presenter."
I think the way that Aaron presented his methods I like, so I'm gonna try and do that. Try and just give a name to each equation, and perhaps instead of defining each one at the end, like what each letter represents, define it after each equation would probably be a better way to do it, so that you don't have to go hunting for them. Okay, so as far as results go, the mechanism for the formation of water was determined. You can see here there's 3 main reactions that are occurring with the formation of water, and so the question arises: are these reactions that we're visualizing using VMD accurate? Or can we trust them? Because VMD, they display these bonds based off of distance. So if 2 atoms are within close proximity to each other, it's assumed that they're bonded to one another in most cases. So it's important to look at electron density, and looking at the bottom panel of reactions there for the formation of water, we can see on the 4th panel that the electron density cloud surrounds the water molecule specifically. So we know that the formation of water occurs just from...
Can you circle water?
Yes.
Let's cooperate on this, because I haven't learned how it works. Sometimes this panel appears.
Okay, so there we see the water. Here we see the water. Okay.
So you may do it on poster as well.
Oh no, I didn't mean to make that line. Yes, okay. How do I get out of this now?
Maybe instead of pen, select like highlighter or laser pointer.
That's cool. Okay.
Or maybe just escape. In worst case, it will just save and start presentation over. If you do
I don't know why my slideshow kept those animations, but alright, so we can see the formation of water. This mechanism is consistent with just the first water molecule that's formed throughout the combustion mechanism. So this actually needs to be changed as well. My graphs here on the bottom, the top one corresponds to actually the last molecule of water that's formed, not the first. There's 3 that's formed throughout this 1-to-1 ratio on a 500 femtosecond process. So this blue line represents the distance in angstroms between the oxygen from the water molecule and the hydrogen which it accepts to create a water molecule, and the red line represents the nitrogen which donates its hydrogen and the distance between those 2. So we can see that as the distance of the blue line approaches 1 angstrom, the distance of the red line goes to infinity, in theory or whatever. But so when it reaches 1 angstrom is when the water molecule forms. What's important that I don't have on here is the total energy of the system when this occurs. So the formation of water is an endothermic process, and that can be proved by looking at the total energy of the system, and that will be outlined on my poster Thursday. On the bottom graph, we see theoretical mass spec. So by taking each time, sorry,
Theoretical or computed by your own data?
computed by my own data.
So highlight it,
Okay.
because theoretical has some ambiguity.
Simulated mass spec.
Yes.
Okay.
So original simulated data from this trajectory.
Okay.
Otherwise, like maybe there is a theory in a smart book or
Yeah.
journal.
Okay. So yeah, simulated mass spec. So we can see all products which are formed throughout every time interval of the combustion mechanism. We see.
Sorry for interrupting. Can you indicate where are the reactants on this mass spectrum?
Yes. Okay, so I will just say right now for the purpose.
You can just show it there.
Yes. So the very last peak that we see here, around 93 or so, is the nitrogen tetroxide molecule, our oxidizer, and around 34 we see our hydrazine peak, which is the second largest peak on the mass spec here, which indicates that it is the second most occurring molecule behind nitrogen dioxide, which is a product of dinitrogen tetroxide breaking down.
Would it be correct to say that if you freeze your simulation cell to like absolute zero, then after long time there will be only peaks corresponding to reactants
Correct.
and no products developing?
Correct. At absolute zero, yes, there should not be any movement, so that the molecules should stay in their original.
So you can even highlight the reactants with different color, or just put lines, artificial bars. And again, same as with Aaron, you will be a teacher for most of your visitors.
Okay.
They will not doubt your knowledge. They will try to understand what you mean by short time. So do not hesitate to teach very simple things.
Okay.
Appeal to their common sense.
Okay. So overall, the important things to take from this study is that we now know the mechanism for the formation of water, a step-by-step mechanism, as well as we know we can give a variable, or I don't know if that's the right word. We can label, I guess, the byproducts, not just the end byproducts, but the products throughout simulation. So those which occur for only a short time, as well as those which are stable configurations, which stay in. One of the most stable ones, which don't decompose, is water. So the more water that we have, the more stable our reaction fuel is, and if we could get the max amount of water by changing the ratio of fuel to oxidizer, it would decrease the amount of toxic byproducts which form. Another future plan for decreasing toxic byproducts would be introducing catalysts such as platinum nanocrystals.
Okay, let's thank Dane. So do you have questions?
John?
So, and I think you may have mentioned this, but so are you using just standard molecular dynamics that come available from VAF software to run these simulations?
Yes.
Okay. And do you know what the actual pressure is? I know you give the temperature and the volume, but I didn't know. Do you know what the calculated pressure is for the system?
I have it. I don't off the top of my head.
Okay. And then my last question is, so in terms of your simulated mass spec that you show, right, that's a summation of fragments along the total trajectory.
Yes,
Okay.
Yep.
Okay.
So,
And then,
go ahead.
well, no, you can answer first.
I was gonna say, so like Yulin was saying with his mass spec, it takes a snapshot at each time interval and calculates fragments and then compiles them by their occurrences.
Okay. And then, just for curiosity, had you ever considered if you just take the mass spec from your initial system and plotting it on the same as your final mass spec from the dynamic trajectory? That way you could show, the drop in product or reactant formation or reactant molecules, just to show.
Well, I don't know how much that would bring to the table, simply because we only have 2 molecules to start out with. I mean, we may have it's a 1-to-1 ratio, so the intensity of them is going to be, there'll only be 2 peaks. So it's expected that those peaks should decrease through time because it's a hypergolic fuel. There's no requirement of energy input in order to get this ball rolling.
Okay.
Do you agree with that? Or do you think?
Well,
do you think that having like a before and after, is that what you're saying, of the mass spec?
Mm-hmm. Right, because you have a chemical reaction occurring, so there should be some type of new product forming and a decrease in the number of potential reactants, right? Because it's not like you have an actual catalyst that sustains its own number of molecules through the reaction.
Well, I think it's important to note that this mass spec isn't the number of molecules which exist, it's the occurrence of molecules which exist. So if you were to take a mass spec at time step initial 1, you would see equal intensity peaks of hydrazine and nitrogen tetroxide. So I see what you're saying, but I don't know if a graph of that would explain better than simply this picture, Because if you were to take a mass spec of time step 0, you would just have 2 peaks, right?
Yeah, potentially. If that's the only thing.
Oh, you're saying, okay, I see what you're saying. So instead of taking a time-dependent mass spec, you're saying take an image of time step 0 and an image of time step 500 and compare those two?
Well, so the mass spec that you have here, you have how many different peaks, right? Because you have things fragmenting, you have products forming. If you would plot a mass spec of just time 0 on top of that, you should, like you said, see 2 peaks of your 2 products of equivalent value, but none of the other peaks would exist.
Right.
And so I didn't know if that would graphically help, the idea of, yes, we do see all of these things forming, rather than, some of just the snapshots. But
so, as I understand, John is not trying to criticize. He suggests tricks that will help intuitive understanding for general audience. A reference point.
So have just a red line to the top of the graph at N2H4 and a red line to the top at N2O4, and say red is initial products and blue is all occurring fragments throughout the simulation. Yeah.
Right. It's just a really quick thing you can put in, and it gives people an idea of what's actually occurring if they don't feel like sitting and reading everything.
Right. No, absolutely. And that is another point. So with my presentation itself on the poster, how do you guys feel about having these paragraphs of words? Is that too much?
It's fine. Oh, but other.
You think, or is that okay to leave what I have? I mean, like I said, I have 23 sources right now listed there. So
Well, if you do not give them in your bibliography, then you cannot cite thing. You cannot give a number if you do not decompose it into full citation.
and so I mean, I'd have to have a list of 23 in my bibliography.
And you will not have a place to do it. Just
Right.
select something more important.
Okay.
And do whatever you feel comfortable. It's not last time in your life you do poster. You will just gain experience, and you will see people behaving like zero understanding, square eyes, like what is it here? And the next time, and then you will see that if you point and guide people, they understand better. But there are some old-fashioned and biologically old people who prefer continuous, grammatically correct text, but typically they are in minority.
All right.
I don't know, my undergrad advisor, he said paragraphs are stupid for posters. So
Okay.
that's just some people's philosophy.
Sounds good.
When I was doing a postdoc, I was trying to do broken bullet points, and my advisor was always like tearing last hairs from his 70 years old head, and I do not understand. Do complete sentence. So there are different opinions. Can I contribute?
Yes, please.
So it is for John. You see this average? I'm trying to point in the equation 6.
Yep.
So the well, one equation is missed here. The equation, and you didn't change the notation. So equation 5, if you put it here,
Yep.
should define this mass spec as function of mz at time t,
Yes.
which will include the delta function of mz minus mf
Yeah.
of t, right? And summation equals ms of t. But then what is shown in equation 6 is an average over the whole trajectory. So it is not time dependence, but it is integrated time dependence.
Mhm.
So even if by the end of reaction there are no reactants in the simulation cell, the final
Would still
result
show
will
up.
Still show them. And
Yep.
this is made for the following purpose. If you look for number of molecules of, let's say, reactant, it will be very, very, there are just 4 of them, and it will show like weathers down, or it will show some discrete oscillations that are kind of strange. And this average makes something more reasonable,
Yeah.
which can be
No, but-
interpreted as there is a ensemble of reactions going in parallel, and one reaction stopped earlier, another stopped later, and we give some average outcome.
Mhm. So basically, you use the same type of idea with these ensemble trajectories, kind of like Ulun is doing, but you don't implement like Rabi oscillation cycling.
Correct.
Okay.
So the post-processing is the same as in all works by Ulun, but the engine is a little more simple. It's regular molecular dynamics instead of TD-SMD.
Mhm.
more questions to Dane? If not, thank him once again. Yes, yes. So good luck with collect feedback. John, if you have some feedback, please email it directly to authors.
Okay.
So good luck with completing your posters, and please figure out how to print and where to post them. Even if you are not presenting, you are welcome to stop by and watch group members and other presenters. I don't think anyone will check if you are registered or not. This should be like open.
Where is it located? Is it in the Prairie Room and upstairs of the Union?
I wish I know. It will be a big. I'm not very organized. I will be figuring it out at last minute. I also need to present there, so I will be just running with the computer and looking like which room should I be.
I believe I said it was the Alumni Center.
Okay.
Oh, the alumni center is. They have less rules. Some things that are forbidden in Memorial Union are allowed in alumni room.
Yeah, you can drink in there.
Okay, and so good luck in presenting. Many thanks for collective contributions. Meeting is dismissed, and I will ask by personal emails help with proposal development.